with energy diagrams. So the energy is on the y-axis, and the reaction taking place is on the x-axis. And so if we have a reaction or a graph that looks like something like this, well, that shows us a few things here. So this is like our product, and this is our reactant. Or I should put the reactant maybe on this side. Our reactant starts here. Okay? And so what kind of reaction does this look like? Exothermic or endothermic? Look at the energy. This is the energy right here. Are we releasing heat or absorbing heat?
So is that exothermic?
Yeah, this would be exothermic because we start here and we end here at a lower number, right? So this is exothermic. Now let's take a look at the change in G, or Gibbs free energy, right? Delta G is the change in energy. Do you guys know how to find a change in anything? For example, change in temperature is equal to final temperature minus initial temperature. You guys understand this? Or if we have a delta little t, that's final time minus initial time, right? We could do this with anything. So we could do it with energy as well. Well, here's our final energy, and here's our initial energy. Our final energy is a small number, minus our initial energy is a big number. So that is a negative value. So delta G is less than 0, or it's a negative delta G. So making this spontaneous or non-spontaneous? Negative delta G is spontaneous. Now let's take a look at the graph and make sense of why this is spontaneous. Okay? Now, this right here is called the activation energy. And I'll just say E sub A for activation energy. And this is the energy, like when we talked about burning gas last time, right? This is the little spark it takes it to get started, right? So it takes a little bit of energy to get it to react. But just think about, we have a ball here, and it takes a little bit of energy to get the ball rolled up the hill. Once we have it to the top of the hill, what can happen? It'll just roll down all by itself, spontaneously. Does that make sense? So then it's just going to go down here all by itself. Spontaneous. Does that make sense, guys? Okay? All right. Why don't you see if you can draw one that is endothermic and non-spontaneous? If you can't, no big deal, we'll get there, but try it. Still energy on the y-axis and reaction on the x-axis. So where do we start? It doesn't really matter where we start, but where do we go? We should go up. It takes energy. We're going to absorb this energy. So you might not have had that last curve, but you still have to have an activation energy, right? So for example, or for, let's just, so this right here is our change in energy, or our delta G. And here this is our initial, and this is our final, right? So final is a big number, minus initial, which is a small number, makes this a positive delta G. It's greater than 0. Does that make sense in everybody's mind? Okay. That makes it non-spontaneous. And we start giving it energy. If we quit giving it energy, what's going to happen? It's just going to roll back down. Nothing's, right? It's not going to go through. It's not going to continue. So we have to keep pushing energy, keep giving it energy, because it's non-spontaneous, until it gets to here. But then it can go down this little hill, right? So this is still our activation energy. We have to get over that hump to get it to react. Making so, since we have to input energy, that makes it endothermic. Are we okay with that?
Would there be a depiction where the graph plateaus and maintains that, or no?
You mean something like this?
Well, like even like, so in the endothermic non-spontaneous, how it comes up, drops down that little hill, and
Uh-huh.
there wouldn't, no, that doesn't make sense, because.
It could maintain. You mean just stay there?
Just to like, stay there.
Yeah, and if it does, we don't really, we usually just stop it right there, because it,
Change.
yeah. Because this is really the only part we're interested in. Good?
Yes.
No, thanks for asking. All right. So now let's draw a reaction. What would determine if a reaction is slow versus fast? The slope of it? Okay, good. Any other thoughts? It's all about the activation energy. Okay? If we have a large activation energy, that means it takes a lot of energy to get it to react, right? So we have to keep putting energy in it, keep putting energy in it to get it to react, and finally it'll go over that activation energy, right? And then it will react. So that one is a slower reaction. So the slope, I mean, that's a great thought, but this reaction here, we can draw squished to fit in our page, and that really won't affect anything. That's just, this is kind of like our time, right? Well, not really, because if it was, then if it's stretched out, then it's a long time. So yeah, it's just our reaction, and we don't really put in time there, so the time really is affected by the activation energy. So if we have a small activation energy, then it's going to be much faster. Does that kind of make sense, talking about these If it doesn't take that much energy to get it to react, it's just gonna react quicker, right?
So like the spark.
Yeah, that's a little spark is gonna be small activation energy, right? You don't need that much at all, then it's just gonna, okay? All right, so if we draw these, in fact, I want you to tell me what you think this is. Fast or slow? So again, remember this is where it starts. This is where it ends. So there's my delta G. And right here is my activation energy, right? Large activation energy, yeah, so it's going to be slow. What would it look like if I drew one that's quick? Something like that, right? Where we have a low activation energy. And I can write this endothermic or exothermic, doesn't matter. But if we have a low activation energy, then it's fast. If we have a large activation energy, then it's slow. Good? Okay, let's go to our worksheet from last time. And if you didn't get one, I have some up here still. Just leave a quarter on the table. Did you need one? Oh, okay. Let's take a look at section 6 on the back. It says, draw two energy diagrams. On the first, show a reaction which is exothermic but very slow. And then on the second one, show a reaction which is endothermic but very fast. Make sure you can do this on your own if you can. This part on the exam will be cinch, right? If not, we know what we got to study. We good? Or should I give you a minute? So something like that? Any questions? Does it have to look just like that? And I think on the test, it's they're going to give you a graph and you're going to have to say whether it's fast or slow or exothermic, endothermic, all that stuff, okay? And Seems like it was a little bit, I mean, it's all relative, isn't it? So it's fast if your little activation hump is tiny, okay? They might not be, it might not be as exaggerated as this one for a large activation energy, okay? So if you, did anyone draw it lower than that? Yeah, and that's okay. It's just all relative. So if I draw something like this, that's going to take longer than this one still, right? Okay. We good? All right. Any questions on thermodynamics? No? All right. Let's move on to equilibrium then. Or first of all, let's talk about the collision theory. Here. All right. So if atoms are, for a chemical reaction to take place, or maybe I should write that. For a chemical reaction atoms or molecules must collide. Does that make sense? If you had atoms over here and they're just not really hitting each other, they're not going to change, right? So they have to collide in order to react. Make sense? Okay. And the collisions, collisions must be, at specific orientations. So, for example, if we have a molecule that looks like this, and we have another molecule that looks like this, will we get molecules that look like, or a product that looks like this? This kind of goes right in here. It's not oriented the right way, right? It's got to be flipped more like this, right? Does that make sense? So it's got to be oriented the right, needs the right orientation to get this thing to react. Good? And you have the molecules are atoms. Atoms are molecules. Must have sufficient energy, amounts of energy. If they just come in here and bounce, dun, they're not going to really react, right? They got to really get in there. Good? Have enough energy to react. Does that make sense so far? Any questions? Okay. Let's talk about what makes a the rate of chemical reaction faster. What increases the rate of reaction? So in other words, what makes things react faster, right? Any ideas?
Biology, it's enzymes.
Okay, yeah, you add a catalyst, right? Yeah. Add a catalyst. Catalyst. And this is the more difficult one. But yeah. What does a catalyst do? Let's write this definition. Catalyst is something added to speed up a chemical reaction. That's it, right? Or making it possible to react, right? So enzymes in our body are, right? What about a catalytic converter, right? You know what that is? It's a part of your car that allows the combustion of fuel to completely combust. That way you don't end up with these bad gases, right? But all it is, well, anybody hear about people stealing catalytic converters off of cars? Why do they do that?
Cadmium?
Is it cadmium or is it platinum?
Can't remember. Something expensive inside of it.
Yeah, I think it's platinum. And that's why catalytic converters are so expensive, right? People rip them off your car to get the platinum off of it. Well, then your car doesn't work, dang it, right? Well, it works, but yeah, doesn't pass emissions anyway. Okay. But what that does is it allows it to react quicker or completely, right? So it's an additive that speeds up the reaction. And not only does it speed up the reaction, it doesn't really change what the kind of did, I guess, but it doesn't affect the end product really. Okay. Anything else that speeds up a chemical reaction? Temperature. You increase the heat, what does that do? Makes the molecules do what? Move faster. If they move faster, they're going to do what more? Collide more often, right? And with more energy, right? So increase the temperature. Will increase collisions. What's another way to increase collisions without increasing temperature? You stir it, right? Stirring will also increase collisions. Another one is increasing pressure. What does increasing pressure do? Forces them together, right? More collisions again. Does that make sense to everybody? Okay. Okay. And so when we add a catalyst, let me just add one more thing here. When we add a catalyst, it lowers the activation energy. And we know we talked about the diagram, when we have a small activation energy, it goes faster, right? Any questions about the collision theory? How reactions happen? How you can make them quicker? All right, we'll get into that maybe a little bit more toward the end and kind of help tie things all together. But let's get into equilibrium. You guys ever hear of equilibrium? What does that mean?
Isn't it?
Balanced. What? Go ahead.
No, I was gonna say, isn't that what they, well, maybe you're wrong, actually, never mind.
Oh, no, that's okay. It's okay to be wrong.
Isn't it, I swear, I feel like in our chemistry lab, it was about how we measure like heat, or I might be wrong. That doesn't make sense, because I remember I went to an ear doctor, and then he was like, oh, we need to make sure that not use that word, or else you walk like.
Yeah, that's right. So, yeah, there's something in your brain that keeps you in balance, right? And I don't know what it's called. It's like a gyroscope, but
The semicircular canals.
yeah. And if that's off, then you lose your balance, right? So, yeah, you're kind of in equilibrium. And things in nature tend to go toward well, not always, but okay. We talked about going to more chaos last time. But so if let's say you're home and you're working late, it's like, just want to cook something quick, right? So you make spaghetti, right? You put a pot of water on to boil to make spaghetti, and you're talking to your spouse saying, let's just go get pizza. And what do? You shut off the heat and you go get pizza, right? Actually, nowadays you just order pizza, whatever. Okay, it's just, anyway, so you got boiling hot water, and you turn it off, and what happens? It cools down to room temperature. Does it get colder than that? No, it just cools down to room temperature, then stops. What happens if you're cooking a lot in one day? What happens to the temperature of your house? It increases, right? So there's something called thermal equilibrium, and that's kind of what happens just by nature, right? Things tend to go toward thermal equilibrium. Hot things will go to more cold things, and then it just kind of keeps everything the same temperature. And so when we talk about chemical reactions, kind of the same idea, but only with reversible reactions. So when we talk about equilibrium, we're talking about reversible reactions. So I'm just going to draw a simple generic equation. A plus B and that's lowercase letters are like the coefficients in our balanced equation, right? And then the capital letters are like our substances. You with me? And we write a reversible reaction with a double arrow, one going in the forward direction, one going in the reverse direction. And if you'd like, you can draw it like this, no big deal. But it's just a little bit quicker to draw it like the way I did down here. And then you got CC plus DD. Good? So this is saying we can mix A and B together and we'll get C and D. And if we get too much C and D, well, they're going to collide together and then make more of A and B, and then just keep going back and forth until what? They reach chemical equilibrium. Does that make sense? Now, when we deal with equilibrium, we want to make predictions, right? Just like we did with stoichiometry. And there's something called the equilibrium constant that helps us make more predictions. Okay, so here it is. Equilibrium constant K is equal to, and I'm going to write something here real quick. If I write a bracket with substance A in it, this refers to concentration of substance A. Yeah? You guys understand what concentration is? So if something's highly concentrated, what does that mean? Yeah, you got a lot of solute compared to solvent, right? Well, maybe that's words that we haven't talked about yet, right? But it's, let's say, you guys heard of concentrated orange juice, right? You guys ever make that? Yeah, it's a frozen can of orange juice. You just dump it in and dilute it with water, and you mix it up, and you have plenty of orange juice, right? And if you're on a budget, then you put more water in, and no one wants to drink it, right? Okay, whatever. Okay, but concentrated means you got a lot of it there. So before you add water, it's just tons of nice and sweet and plenty of orange content in there, right? Okay. So this just represents the concentration of substance A. Okay with that? All right, so here is the formula that you're going to have to know for the equilibrium constant K. It is the concentrations of the products raised to the coefficients of those products, power, does that make sense so far? So you take the concentration of C and raise it to the coefficient of C. And you're going to divide that by the concentration of the reactants raised to their powers, to their coefficient power, multiplied together. So we need to get this down. This is not on our reference sheet. So we are going to just have to either put it on our little note card or memorize it. Products over the reactants. Okay? So let's try this. Let's set it up on a simple equation first. If we have 2NO2 reacts in equilibrium with N2O4. So this is the simplest, as simple as it gets. K is equal to what? The concentration of what? What?
Solution?
Of our product. In this case, our product, there's only one product, so it's N2O4, raised to what power? 1. The coefficient in front of N2O4 is 1, since there's no number, right? So we don't even have to write to the 1 power, because it doesn't really change anything mathematically, right? Divided by the concentration of our reactants, in this case there's only 1, raised to what power? 2, the coefficient of that reactant. You with me? That's it. You guys ready for one on your own? I know that was an easy one, or should we try one more together? One more together? Okay, let's do 2NOBr reacts in equilibrium with 2NO plus Br2. So K is equal to, again, we start with the products, the concentration of the first product, which is NO, raised to the second power because of that coefficient. You with me? Multiplied by the concentration of the second product. In this case, the coefficient is 1, so we don't need an exponent. Divided by the concentration of our reactants. In this case, there's only one reactant, raised to the second power because of that coefficient. Make sense? Good, because we have to be able to do that before we can do anything else. So let's practice section 7. We got A, B, and C. You guys okay on your own, or do you want to try some more together? How you feeling? Yeah, give it a shot. Looks like everybody's on their phones. Are we done? Okay. Is this what we got? I don't care if you're on your phone, but is this what we got? All right. We good? Any questions? All right. So now let's, if we understand that, now we can start putting numbers in, right? You guys ready for this? It's just simple, basic algebra. Nothing too fancy. But let's go ahead and try this. So there's a couple of different ways we might get it. We might get it to where we have to calculate K, our equilibrium constant. And we might be given our equilibrium constant. We might have to calculate a concentration of one of our substances. Okay? And I think in general, the second one is the most likely one that we will be doing. Because we can go look up all the equilibrium constants. Some scientists have already found them out, right? So we're just going to use the equilibrium constant for a specific reaction to find out, okay, if we know this concentration, we can predict what concentration we should get, right? For an unknown. So let's go ahead and do the simple one first. So if we have, we're going to do this, use this equations for both of them. NOBr reacts in equilibrium with 2NO plus Br2. And we already wrote this equilibrium constant reaction, or equation. So it's K equals concentration of NO squared times concentration of Br2 all over concentration of NOBr squared. Good? All right, so if we know we have concentration of NOBr is equal to 0.0158 moles per liter, and that's just the unit of concentration we'll use. We'll get into concentrations more next unit. And the concentration of NO is equal to 0.1 moles per liter. And the last one, concentration of Br2 is equal to 0.05 moles per liter. So since K is already solved, it's all by itself, we don't have to do any algebraic manipulation. We just plug our values in and multiply and divide, right? And don't forget the squares, the exponents, right? So we put in parentheses the concentration of NO, which is 0.1. Don't forget we must square that. Multiply the concentration of Br2, which is 0.05, and it's just raised to the first power, so we're good there. Divided by the concentration of NOBr, which is 0.0158. And don't forget, we better square that. Make sure you can type this in your calculator okay. It's not difficult, but you got to follow order of operation. And our K equilibrium constant should be 2. And there aren't any units for equilibrium constant K. No units. The units cancel out, so we're good. It's one of the few things that don't need units. Does that make sense in everybody's mind? Ready for a tougher one? Or not yet?
Can you do one more like this, like a little harder one?
Yeah. Okay, let's say we have, so what part is catching you? Is it the calculation of it, or is it the equilibrium constant equation?
I think I'm good with the equation. I think the moles per liter is probably the goal.
Okay, so moles per liter is just a unit of concentration. It's not the only unit of concentration, but when we put it in here, notice I didn't even put the units there. Why not? Because they're going to cancel out anyway, right? All the units cancel out, therefore no unit left over. So really you don't have to worry about the units. So I just plug the numbers in that I have been given, and you will be given those if you're looking for K, okay? How do you feel?
Better because you know the units.
Yeah. Now, in the end, we might be looking for a concentration, and then we cannot, and we have to know the units, okay? It's something we just need to be able to do. But for this particular one, they're all going to cancel out anyway. Good? So are you good with just moving to the next one? It's not too much, it's not too difficult, but yeah.
I'll let you finish.
No, we're good.
So, on the exam, are we gonna have that roadmap where it goes from grams to moles?
Yep.
To the coefficient?
Right
Are you
there.
gonna provide that for us?
Yep, it's right here, and you're given this sheet.
Perfect.
Yep. But this sheet does not have this equation up there,
No, that's fine.
okay?
That's fine.
All right, so let's use this same reaction, but a different problem. Let's say, so we're using the same reaction. We need to calculate Br2, the concentration of Br2. That's what we're looking for. And we know the concentration of NOBr is 0.016 moles per liter. And the concentration of NO is equal to 0.1 moles per liter. So we're going to use this equation right here one more time. Whoops. Okay. Now, what are we solving for? Br2. We need to get Br2, concentration of Br2 all by itself. Now, ladies and gents, you could plug numbers in and then solve if you like. And that's the way that we learned when we was in junior high, and so that's the way that's stuck in our head. But let me tell you something. It's much more simple to do it without plugging the numbers in first. And we're going to be doing this next unit a little bit more. So let's practice it right now. Doing it, calculating or solving for the unknown variable without numbers. Because remember, math works the same with variables and with numbers alike. Okay? Are you good with trying this with me? Okay? Because I remember when I heard this, I was taking physics for engineers, and I was so used to just plugging the numbers in and then solving. And the TA says, okay, let's do it this way. I say, yeah, no, I don't like that. He says, it's way easier. I say, I'll try it. So I tried it and think, yeah, this is way cooler. It just is. And it's a change, so you have to get used to it, but all right, so we want to get concentration of Br2 alone. So what do you want to get rid of first? the fraction. Let's get rid of the fraction, because who likes fractions? Anybody? Yeah, we don't. So this says divided by the concentration of NOBR squared. So how do we move it to the other side? Inverse operation of divide is multiply. So we're going to multiply both sides by NOBR squared. Everything. Don't forget that squared. You with me? That goes away. Whatever we do to the one side, we better do to the other side. Otherwise, it's not equal anymore. So we're going to multiply by the concentration of NOBR squared to both sides. And then I can rewrite it so that it's not too messy and you guys can still follow me. Everybody understand what I did? Okay. Now we got to get rid of this. What's being done between those two? What's the operation? Multiply. So what do we do? What's the inverse operation of multiply? Divide. So we divide both sides by the concentration of NO squared. That goes away. And we're left with the concentration of Br2 is equal to the concentration of NOBR squared. Multiply the equilibrium constant K divided by the concentration of NO squared. You guys okay that I put Br2 on the left side? I kind of just flip-flopped it. Okay? All right. Now we have an equation, solve for what we're looking for. Now it's just as easy as the last one, right? We just plug the values in and multiply and divide. And don't forget to square, right? So our NOBR is 0.016. And again, I can omit the units because they're going to cancel out, right? Don't forget to square that because of that guy. And what's our K? We figured that out in the first problem, right? It's the same reaction. The equilibrium constant is for a specific reaction. And it's going to be the same constant for that reaction, whether it's 2,000 years ago or 2,000 years from now, as far as we know. Okay? So that's going to be 2 there, divided by the concentration of NO, which is 0.1. Don't forget, we've got to square that. Then we follow order of operation to find our answer, and we get the concentration of Br2 is equal to 0.051. In this time, since it's a concentration, we must include the units. But it's going to be whatever concentration unit we started with, right? Does that make sense? So again, we don't have to write the units while we do the math, but just know we're looking for concentration, but we've got to know what unit it is. How do you feel with this? Yeah, Kai.
So how's, I mean, obviously it's new to some of us, but how is that different from plugging in the numbers?
Mathematically, nothing. It'll still work.
It's just not gonna work in like the next chapter or?
No, it'll still work. If you don't like it, if you don't like to solve before you plug numbers in, then don't. Plug the numbers in first. It still works, but if you have a bunch of numbers all over the place, think it's easier to make a mistake somewhere, maybe forget a 0 or forget a something. Right, I mean, you can still forget something if you do it this way too, don't get me wrong. So, but yeah,
Just an alternative.
yeah, you could do whatever way you want. Yeah, it doesn't matter really. Yeah,
So given that, so obviously we did the same reaction above, so we knew what K was going to be.
mm-hmm,
But say we had a problem that was like, yeah, we don't know what.
then
concentration
I
for
will
this.
give you K.
K will be provided?
Yep.
Okay.
Yep.
I was gonna say, like, well, we have to find K first, then. But if we were to find K
Possibly.
first, it's the top.
With 2 problems, possibly.
Okay.
But I don't think I'd do that on a test. I don't think it's like that.
Okay. Cool. Thank you.
Mm-hmm. Are we good? You want to try some more? Okay. On section 8. So the first part, A, you're looking for equilibrium constant K. And then part B, you have K and you're looking for concentrations. So you have both types right here. Give it a shot. And by the way, our time is good compared to my last class, so are we feeling okay though? Okay. So just go ahead and try this, and we can do it all together if you need. I'll post the answers in a minute. Okay, the answers are up here. You wanna check, see what you did? If you have questions, let's go over them. Any questions?
I'm just not getting that,
The answer?
yeah, like I'm plugging it in my calculator,
This one right here?
yeah,
Okay, so you're putting 0.11 squared. Are you just not getting in scientific notation?
yeah, I'm not, maybe it'll be better if I do that. No, there, so it's different. Getting 2.904.
Okay, let me try it. 0.11 squared divided by, and then you gotta put in parentheses, 0.025 squared multiply 0.015 and parentheses. And yeah, 1290.7 or 1.290 times 10 to the 3. So that's correct. All right. So you got to remember, ladies and gentlemen, that your calculator is just a machine, and you have to tell it to follow order of operation.
So where am I?
So this
Sure.
parenthesis, I mean, you can get rid of that and put squared right there. And then times the
The 0.015.
0.015. Because what you said is this divided by this and then times this.
Oh, okay.
So easy to do.
That makes sense.
So
Okay.
when you put it in parentheses, I'm gonna just write on the board how you should put it in your calculator. So is this color okay? 0.11 squared divided by, in fact, you probably just push the divide button, right? Divided by, and then in parentheses, 0.025 squared times 0.015. So you have to do all of this together, because this is kind of like, you got to do all of that first, parentheses first, before you do anything else. Good? Any other questions?
With the, part B,
Yeah?
I just kind of, I was like, because we did it the one way where it was like no numbers, and that kind of confused me, so I'm like, I'll just try to plug in the numbers.
Okay, good.
And then I lost myself. So,
All right.
do you mind, like, going through that one,
Without plugging numbers or with plugging numbers? With?
please?
Okay, yeah, you bet. So, just the first one or both?
Yeah, just the first one, it's fine. Just give me a second.
Okay, so we have our equation K equals NO2 squared over N2O to the fourth. Okay, and I'm just going to plug the numbers in. So we got 0.0250 squared, divided by N2O4, and that's what we're looking for, is equal to 7.2 times 10 to the negative 3, right? Okay, well, it's because maybe this is on the bottom and we got to get it on top, right? So we can cross multiply, right? Or it really don't have to. We just multiply both sides by N2O4, right? So if we do that to both sides, N2O4, that goes away. Multiply this side by N2O4. And so we get 0.0250 squared equals 7.2 times 10 to the negative 3, multiply the concentration of N2O4. You follow?
Okay.
And maybe if you do one step at a time, then rewrite it, make sure it's clear. And then we divide both sides by 7.2 times 10 to the negative 3. And that is equal to our concentration of N2O4. Make sense?
Yeah.
So, yes, you can do it by plugging the numbers in. So, if I made you feel like you have to do it my way, you don't. Yeah, you could do it this way, that's fine. Good? And then just make sure you square this first. And then when you type this in, if you're not sure if you're doing it right, put parentheses around all of that stuff. Okay? It depends on how you type it in and how your calculator. Some calculators, if you type it in with that EE or EXP, then you don't really need parentheses, but parentheses are still okay, right? Good?
Makes sense, thank you.
Does anybody need to go over part II? So that one we're going to have to square root when we're done, right?
What was the answer?
Oh, so the answer on this one is 8.68 times 10 to the negative 2, or in other words, that's 0.0868, right? Moles per liter.
We have to do the square root on that one because the NO2 was squared.
Oh, so yeah, because we're going to multiply both sides by 0.075, right? And then we have the square here, so we have to square root that to get rid of that square. Good? Questions? Do we want to go over any of that? All right. One more idea and then we're done with new stuff, with all the stuff for this exam. And our exam is on Tuesday, right? Okay. So the last thing is called Le Chatelier's principle. Some French guy. And what this is saying is if a chemical system at equilibrium experiences change, then the equilibrium will shift to counteract the imposed change. Now that's a lot of words. Should I just show you what it is? Okay. So I'm going to take a simple equation because I don't want to write all the icky, yucky stuff. Are we okay with that? So if we have 2NOBr in equilibrium creates 2NO plus Br2. So there's three things that we need to know with Le Chatelier's principles. So the first one is concentration. If we increase the concentration of, let's say, one substance, if I put more of that of NO, so this is like one big pot, right? You guys understand that? You don't have a pot over here and a pot over here, right? It's all together. This reaction is happening in one container, you might call it, okay? So if we add into this container some more NO, what's it going to do? It's going to react with all of the Br2 that's there, right? And so which way is the reaction going to go? It's going to push it this way to make more of our reactants. Does that make sense? If we were to increase the amount of NOBr that we have, then it would push it in the forward direction to make more NO and Br2. Does that make sense in your mind? Anybody have a question on that? So concentration, if we increase one, it pushes it in the opposite direction maybe, right? Pushes reaction to produce more of the other side. Good? And we'll go through some more examples here on our worksheet. And I think if we just talk about this, it might click better. Okay? All right. So again, if you have more particles, they're going to collide more and make more of the other part, right? Okay, the next part is if we increase pressure on one part or the other. And pressure has to do with gases. You can't pressurize solid and you can't pressurize liquid much, right? So when you pressurize a system, it's going to affect the gases. Good? So if we have, for example, carbon monoxide is a gas, so we have to pay attention about the state of matter, plus 2H2 is a gas, and in equilibrium we get methanol as a gas. So, and again, this is in one container. So if we pressurize this system, what is it going to affect the most? The reactant side or the product side? Since there's multiple gases in the reactants and only one gas in the product, we're going to affect the reactant side. In fact, we're going to change the reactant side, and so it's going to produce more product. Is that what you're saying? Yeah. So if we increase pressure, these things are going to collide more often, right? These guys are going to collide and produce more product. So you have to find out where the gases are. Good? Any questions on pressure? Okay, and the last one is changes in temperature. And this will change depending on whether it's endothermic or exothermic. Okay? So watch for endo or exo. So let's see here. So we have, let's just, and this is a real simple example. We have liquid water and it produces solid water. And this is an exothermic reaction. It's not really a reaction, but okay. Are we good? If we increase the energy, that means, or increase the temperature, we're making this more. We're adding it to the right side. So which way is it going to go? It's going to make more reactants. You follow? And if you think about it, if we add heat, it's going to melt this ice and make more water, right? And if it's a flip-flop version, and if it's endothermic, we add it, it's going to be on this side, it's going to make more product, right? You follow? You see how they kind of follow the same pattern? You put something on one side, it's going to go to the other side. You put it on the other side, it's going to go back to the other side. Okay? What about catalysts? Catalysts have no effect in equilibrium. It doesn't change it. Okay? So a catalyst will increase the rate of a chemical reaction in general, but for an equilibrium reaction, it won't affect it. Any questions on Le Chatelier's principle? Should we practice the last set on the worksheet then? Or we could just do these together. Let me scan this in, or take a picture real quick. All right, whoops. So in this first reaction, we have the addition of H2 gas. That means we're increasing the concentration of one substance, right? And the H2 gas is on the product side, so which way is it going to send the reaction? To the left or to the right? It's going to send it this way, because they're going to collide more often with those. So it's going to put it in the reverse direction to produce more products, right? Are we good? What about increasing pressure on the second one? What way do you think it's going to go? Which side is it going to which side is it going to increase that pressure on mostly? The left side or the right side? Remember, pressure, you have to look at the gases. There's a gas, and there's a gas. This is a solid. Carbon is a solid. So it's going to affect this side the most, right? It's going to push these guys together. It's going to push it to the left again. Does that make sense to everybody? So you got to watch where those gases are. What if we add a catalyst on the next one? No change. Yeah, catalysts do not affect equilibrium. Good?
So when you say reverse, it means more reactions or more products?
More products. It goes toward it makes more products. Yeah. So we'll say more products here. Thank you. Because I guess I didn't read the instructions all the way, did I? Sorry. Okay, the next one has to do, you have to apply what we learned in different types of chemical reactions to be able to figure this one out. So let's do this one kind of. If we add sodium chloride, do we see sodium chloride here? No, we don't, but what kind of reaction is this? It's a precipitation reaction, because we got this, it's a double replacement reaction, that's what you were saying, right, Andrew? Double replacement reaction, and it produces a solid, okay? So we have this aqueous solution here, and what happens when we throw salt in water? It dissociates, right? So the salt will turn into sodium ions and chloride ions. You with me? And so really, if we add salt, what part is useful in this reaction? Sodium or chloride? The chloride. Because this right here is an aqueous. That means we have ammonium and chloride ions. They're going to dissociate, and so that means we're adding chloride ions over here. Does that make sense? Questions? We're adding chloride ions. That means we're adding more reactants, and then it's going to push it in the forward direction to produce more reactants. More. Uh-oh. I wrote that wrong, didn't I? More reactants on this side. My bad. So on the first two, it's making more reactants. Sorry about that. Making more reactants. We're adding the products, so it's making more reactants. We're pushing it in the reverse direction. I don't know what I was thinking there. Sorry. And so this is making more products in the forward direction. Did I throw anybody off there? We good? Okay, good. Sorry about that.
Sodium just not matter?
No, it's still dissociated in water. And so that chloride is going to hook up with more silver ions to make the only product in this reaction, which is silver chloride. How do we know that's our only product? Because it's the only solid. The rest is just still dissociated in water. Good? What about the addition of heat? What?
It's a catalyst, so it shouldn't do anything.
Heat in an exothermic reaction. We're adding more of these guys, so which way is he going to push it? To the left, right? Or the reverse direction. And it's going to produce more reactants. Are we good? Did that help going through those? All right. Ladies and gents, we have 20 minutes left. That's all we're covering tonight. That's everything for the exam. Do we have any questions on the study guide? Did we look at it yet? Do we still have it? Does anybody need one? So it didn't help to give it to you early? Anybody else need one? So are you guys feeling you want to go? Okay, yeah, whatever you need. You're welcome to go. Yeah, we're done. If you have any questions, if you want to go over any of these together, we can, whatever. Thank you. Take care. Drive safe.
With that last one, looking at it, how would I know that it's exothermic? Because the heat's on the right side.
Because the heat's on this side. That means it's releasing it into the, yeah.
So,
And if the heat's on the other side, it's endothermic. That means we need to give it heat, give it energy, right? It absorbs.
why would, on the third one down, the heat being on that right side, why would that be?
Because all we added here, so this is in equilibrium, but all we added here was a catalyst. And a catalyst does not change equilibrium.
Oh, okay, I was reading heat as the catalyst. Is that, am I correct in that assumption?
No, this is, so a catalyst might be some other compound.
Whatever.
Yep.
Okay, got it.
So for example, if you have H2O2, it will decompose into oxygen and water by itself. It will. But if you add potassium iodide to it, it'll make it go a lot faster.
Okay,
And you'll see it bubble.
okay.
But then when you're done, you'll still get oxygen, gas, and water.
Doesn't change anything.
Yeah, you still get it.
Okay. So-
That's what catalyst does.
Okay, because I was reading, I was like, oh, heat, because that, I'm gonna butcher it, French, principle, heat, like I was thinking heat as a catalyst. You know what I'm saying? So on that-
yeah.
So on that last one. I was
Because
like,
it
oh,
kind of
it's
does
heat
increase the
is a
reaction.
catalyst.
Mm,
And-
catalysts are substances or something that you add to it. Kind of like our enzymes. Where do we get enzymes for our body? In our food that we eat, right? Okay. But yeah, it's just an addition to it. So heat is actually just energy. And usually we're talking about exothermic or endothermic, so.
Okay. And if it's on that right side, if it's in that products, it's exothermic, so I should be paying attention to that.
And if it just says it's exothermic, you know it should be on the right side, right?
Yeah.
And then it's gonna push it that way. If it's an endothermic, the heat's gonna be over here, and it's gonna push it this way.
Okay. That makes sense, thank you. I was just like,
Yeah,
know,
you
because
bet.
heat was right there, and that's a catalyst, why is
Mhm.
it not, no change? Okay, that tracks.
Anything else?
Just, can we just like review the whole everything for, just from
You,
August back?
you bet, no. How late do you wanna stay?
That'd be great. That'd be great.
Don't worry, I just charge time and a half, so.
I'm not making money yet.
I'm just kidding.
Get back from Alaska.
Any questions?
Are you just saying like in the third one, the heat is just part of the reaction in that case instead of adding heat?
Yes. It's just in the equation.
Okay.
The heat is the product of that, and there was a separate catalyst, like, if instead of the word catalyst, it said potassium iodide, then that would be.
Yeah.
It doesn't do anything to it.
So it just happened to be there. It didn't have to be there. It could have been any one of these. If you add a catalyst to any one of those, it's not gonna change it.
Okay.
I am short, but I'm not. I'm just kidding.
Thank you, Professor.
Yeah, thank you.
Thank you.